Let's start looking into the new topic for this week. We're looking at non-homogeneous equations. Up until now, we have always mostly tried to solve homogeneous equations. In particular, looking at second-order ODEs, we have only solved homogeneous equations. Non-homogeneous equations, second order, means that the right-hand side is not zero. What is considered left-hand side and right-hand side? Well, you can shift things around, but when we talk about left-hand side, we talk about everything that has y in there. When we talked about right-hand side, is everything that doesn't have y in it. So there is this categorization of left-hand side and right-hand side that is a bit more general than the single equation you wrote down. So we're introducing non-homogeneous equations by saying that is a situation in which your differential operator is equal to something that is not zero. And we say that associated to a non-homogeneous ODE, there is a homogeneous ODE. So we want to solve the differential operator applied to y equals to g of t, and we keep in mind that we can or should or have solved already the differential operator of y equal to 0. There is an important theorem for second-order non-homogeneous equations. If you have two solutions of the same non-homogeneous equation, so the same L applied to y1 equals to g and L applied to y2 is equal to g, then the difference between these two solutions is a solution to the homogeneous ODE. If you have a set of fundamental solutions, then you can write the difference between capital Y and capital Y1 and capital Y2 as something that looks like a general solution. So C1Y1 plus C2Y2 for some values of C1 and C2. That means that you can create things from the fundamental set of solutions if you know at least one solution of a non-homogeneous ODE. Let's look at the proof of why should the difference between two solutions of the non-homogeneous ODE be anything interesting. Well, first of all, if you have L applied to y1 equals to g of t and L applied to y2 equals to g of t, then the difference between them is equal to 0. So L applied to y1 minus L applied to y2 is equal to 0. But remember that L is a linear operator. Linear means that you can take additions and subtractions outside or inside of the operator. So the subtraction between the operator applied to a thing and the operator applied to the other thing is the operator applied to the subtraction of the two things. In this case, that means that Ly1 minus Ly2 equal to 0, it means that L applied to y1 minus y2 is equal to 0. But L of something equal to 0 means that something is a solution to the homogeneous ODE. On top of this, we know that any solution of the homogeneous ODE is a linear combination of the fundamental set. Therefore, we can write y1 minus y2 as a linear combination of the fundamental set. A new theorem states that the general solution of a non-homogeneous ODE can be written as the linear combination of the fundamental set of solutions of the homogeneous ODE plus capital Y, where capital Y is any solution of the non-homogeneous ODE. So let's think about this a second longer. We can find any solution of the non-homogeneous equation, any specific solution of the non-homogeneous equation. Add to that the general solution of the homogeneous equation. that we know how to build in some cases. And if we sum this, we have the general solution of the non-homogeneous ODE. That means that for linear situations, looking at non-homogeneous equations is not that hard, because we just have to find the solution once and add the general solution of the homogeneous ODE, and we're good. Look also at the fact that is a second order ODE. So a general solution should depend on two coefficients. And the two coefficients are there. They are C1y1 plus C2y2. So this works. How can we build any solution of the non-homogeneous ODE from any other solution of the non-homogeneous ODE? The idea is that while you fix capital Y to be any solution that you can solve, C1 and C2 allow you to bridge the gap between the choice of the specific solution of the non-homogeneous equation and the solution that you're interested in. C1 and C2, we already seen for the homogeneous situation, allow you to tweak. You are allowed to choose C1 and C2 such that they match any initial conditions. And this is what we need in order to stretch any special solution of the non-homogeneous equation into the solution that we want of the non-homogeneous equation. This is a very strong theorem. It states that if you can solve the homogeneous equation, and if we can solve once the non-homogeneous equation, then we're done. So how to solve non-homogeneous ODEs? First of all, we want to find the solution of the homogeneous ODE. We call it the homogeneous solution or the complementary solution. Then we find one solution that solves the non-homogeneous ODE. We're not caring about initial conditions, we just find any solution that solves the non-homogeneous ODE. And then we plug them all together. And we look for the coefficients of the homogeneous solution such that they fit the initial condition that we are interested in.